previous lecture we had talked of the process of transposition, and then FIR we discussed the direct form structure, its transpose structure, the cascade structure and the parallel structure. The parallel is obtained by polyphase decomposition, and parallel in FIR does not lead to a higher speed. Even if it is parallel processing, the speed cannot be increased, but the realization can be made canonic by sharing delays. We took an example to illustrate this. Parallel decomposition, polyphase decomposition is not normally resorted to because it does not give any advantage in speed of processing, but it is very useful in multi-rate signal processing, where decimation and interpolation do reduce the computational complexity. It offers an advantage. And then we said that in linear phase realizations, because of symmetry or anti-symmetry, the number of multipliers can be reduced by an approximately a factor of half, exactly half if the length is even, or half, no, order length plus 1 divided by 2. Okay. Today we talk of IIR realizations. And the we have already looked at one IIR realization, a first order, where we showed how to make it canonic. This can be applied, a direct form canonic. This can be extended to a general order. For example, if I take a third order IIR filter, third order 1 plus, let us say D1 Z inverse plus D2 Z to the minus 2 plus D3 Z to the minus 3, then P0 plus P1 Z inverse plus P2 Z to the minus 2 plus P3 Z to the minus 3. Then we decompose this into two transfer functions, H1 of Z and H2 of Z, where H1 is an FIR, H1 is this transfer function, this is H1, and 1 by this is H2. Okay. We look upon it as a product of an FIR and an IIR. Then we realize H2. H2, obviously H2Z, if I call this YZ by XZ, well, we had called it W, WZ by XZ, then H1Z is equal to YZ divided by W of Z. Agreed? So, if I realize H2Z first, H2Z, we shall get the equation WZ equal to X, I'm sorry, we shall get WZ multiplied by 1 plus D1 Z inverse plus etc. plus D3 Z to the minus 3 equal to X of Z. WZ is just an intermediate variable, and therefore WZ is equal to X of Z minus D1 Z inverse WZ minus D2 Z to the minus 2 WZ minus D3 Z to the minus 3 WZ. Okay. So, the realization would be, I take X sub Z and, well, I have to go to another page, X sub Z summation the output would be Wz. Okay, and Wz I require 3 delays, Z inverse, Z inverse, Z inverse. I require 3 delays corresponding to d1 Z inverse, d2 Z to the minus 2, d3 Z to the minus 3, and I have to feed back after every delay by multiplying by a constant. The first one would be minus d1 minus d1, and there will be other 2 terms here. This goes to the adder. Then the second one would be minus d2. This goes to another adder, and the third one would be minus d3, which goes here. So this is the realization of H2Z. So this is Wz. If I want Yz, then I have to realize also H1 of Z, which is FIR, and that is very simple. That is very simple. P0 plus P1 Z inverse. So Wz I multiply by P0 and then add, this is a summer, P0, then P1 Z inverse, P1 Z inverse, Z inverse is available here. So I multiply by P1, add it, then I multiply by P2, and finally multiply by P3 and add it here. This is the general way of obtaining a direct canonic form for any IIR filter. It is obvious that if the numerator contained a higher degree, if the numerator had, let us say, P4 Z to the minus 4, then we would have required another Z inverse here and a P4. The realization shall still remain canonic. Okay? You could also handle that problem, that is numerator degree 1 higher or 2 higher than the denominator degree. You could also handle it by writing it as an FIR plus a proper rational function. Okay? So the FIR would be in parallel with the IIR realization, and that would speed up the process. Is the point clear? If the numerator degree is greater than the denominator degree, then you write this as FIR plus proper IIR, and this would speed up the process, because the FIR would be typically, if the numerator degree is 1 higher, then it would be a linear factor, all right, in parallel with the proper IIR, and therefore that would speed up the process. So whenever you get a numerator degree higher than the denominator degree, this is a preferable decomposition, rather than adding 1 more delay or 2 more delays and taking feed forward through multipliers. All right. These are some practical points which one should remember. Now, if I, yes.
You said that parallel processing do not speed up in the FIR case.
Okay. If in this case the degree of n was 4 and the degree of d was 3, then you require 4 delays here in the direct canonic. Okay. On the other hand, what you require is, if you decompose like this, this will be of degree 3 and this will be of degree 1, and therefore 1 delay is saved, not in terms of hardware. You require 4 delays, 1 delay in the first order FIR and 3 delays in the third order IIR, but they delay in parallel, and therefore the result would be available after 3 delays, not 4. The processing time would be 3 times the sampling period. not 4 times. If you put a delay here, then it will be 4 times. In FIR, this is not a realization of FIR, this is realization of IIR decomposed into FIR and IIR in parallel. That is how they speed up the process. But in an FIR, totally FIR filter, parallel decomposition affords no advantage with regard to speed. All right. Okay. Now, if I take the transpose of this, well, what kind of filter, what kind of structure do you think we shall get? We will get H1 first, that is the feed forward, the FIR part, then we shall get the. So, it is very easy to draw the diagram, and I will only draw the diagram of the direct canonic transpose form. The transpose would look like this: x of z x of z, then you have the feed forward first, P0, then P1, P2 and P3. Okay. Obviously, you require delays, you require Z inverse, P0, P1 Z inverse, P2 Z to the minus 2, so one more delay here, P2 Z to the minus 2, then P3 Z to the minus 3, so one more delay here, and then you realize H2. So, H2, the output of this shall be y of z. For H2, you require to feed back D1 z inverse. So, you take a multiplier plus D1 or minus D1. H2 requires minus D1. If the denominator sign is positive, then it will be minus D1, and then the same y has to be multiplied by minus D2 for z to the minus 2, then finally minus D3 z to the minus 3, and our realization is complete. So, it is very easy to transpose a direct canonic structure. As I said, there is a value for obtaining alternative structures, because every structure has its own characteristic signature on word length effects and overflow phenomenon, and you should you should explore the possibility of minimizing these two beneaces. If there is overflow, if you cannot check overflow, then you can either take a costly solution, that is change from fixed point to floating point, which is a very costly solution. Fixed point is much less expensive, or you could scale. That is a better solution, because scaling does not require multiplication. Multiplication operation is the most costly operation in terms of the speed of processing. Multiplication is repeated accumulation, addition, and therefore it takes time. Next, we consider cascade. IIR, like FIR, can be realized in cascade, and if the order, we are now assuming that the given IIR is a proper rational function. So, if the order is even, then you require product of factors like this, HIZ, where HIZ is of the form 1 plus beta 1 z inverse plus beta 2 z to the minus 2, and you can you can take alpha 0 plus alpha 1 z inverse plus alpha 2 z to the minus 2. This is not quite a proper rational function, because you can take a constant out of it and have the numerator a linear factor and the denominator a quadratic factor. But this does not hurt the canonicity, because 2 delays you are already using for the denominator. So, there is no harm in having a quadratic factor in the numerator. So, this is with the case if capital N is even. On the other hand, if capital N is odd, then in addition to this you require add the factor a bilinear factor, that is of the form, let us say 1 plus d1 z inverse p0 plus p1 z inverse. Okay. If capital N is odd, if the order is odd, then you require to add a linear factor. I have already told you that all factors cannot be bilinear, because poles and zeros may be complex, and if it is first order, then you require complex coefficients, which is a messy solution. You should insist on real coefficients only. We can also have parallel. Now, the parallel realization assumes importance. Unlike FIR, it leads to speeding up the processing. For example, if you have h of z in parallel, for parallel realization, you decompose this into summation of hij, where each transfer function, each component transfer function is no more complicated than a biquadratic. That is, hij is either a bilinear or a biquadratic. So, at the most you require 2 delays in each parallel path. Even if the order of this filter is 10, the processing time, minimum processing time, if we ignore the time required for multiplication, the minimum processing time is not 10t, it will be simply twice t, and that is the virtue of parallel realization in IIR. FIR, it does not afford any advantage with regard to speed. So, hij is either of the form p0 plus p1 z inverse divided by 1 plus d1 z inverse, or 1 plus beta 1 z inverse plus beta 2 z to the minus 2, then alpha 0 plus alpha 1 z inverse plus alpha 2 z to the minus 2. hij is of the form either this or this, okay, and the speed of processing, minimum speed, is twice t, where capital T is the sampling interval. Let us close this discussion with an example. This example is from Mitra M6.3, and the transfer function given is hz equal to 12 minus 2z inverse plus 3z to the minus 2 plus z to the minus 4 divided by 6 plus 3z inverse plus twice z to the minus 2 plus 2z to the minus 3 plus z to the minus 4. Well, there, as I said, to a synthesis problem, if there exists one solution, then there exists an indefinite number of solutions. And one of the things, one of the straightest things that you can do is to take out a constant from here and make the numerator here of degree 3, the denominator 4. So, this is one possible realization, but let us see what we can do about cascade realization. First thing you do is to write this in cascade as well as parallel realization. You require to factorize the denominator. In parallel realization, you require to factorize the denominator only, whereas In cascade you require to factorize the denominator as well as the numerator, because you have to assign factors to second order transfer functions or first order transfer functions. And in that sense, the coefficients that you use for multiplication are not the ones that are given to you, they are derived, and therefore they are called indirect realizations. Okay? Direct realization is the multipliers are the same as the given coefficients, whereas indirect is if they are derived. In both parallel and cascade cases, you require to factorize at least one of the polynomials, the numerator or denominator, and these factors are always written with a constant equal to 1, constant term equal to 1. That affords easy realization. Okay? And the scaling factor, you take it out, you can always use this as a multiplier, and in this case you can see that the scaling factor is 2. All right, 2 is simply a shift, and therefore it is not a multiplication. If you can, I have done this factorization, it can be written as 1 minus 2/3. So you first take 12 out, 6 out, 2, make the constants into 1, and the others are all fractions, then you factorize. 1 minus 2/3 z inverse plus 1/3 z to the minus 2, 1 plus half z inverse plus 1/4 z to the minus 2 divided by 1 minus half z inverse plus half z to the minus 2 multiplied by 1 plus z inverse plus 1/3 z to the minus 2. Now this is a factorization, this is required for cascade, and the cascading you can do like this. You can make a break here, and you can take this as H1 and this as H2. Okay? This is one possible realization. Nothing secret about this. You could assign this factor to this denominator. Okay? So you get a second realization, and the other ones are you could also assign this factor 2 to either the first one or the second one at the beginning or at the end. So there are many different realizations which are possible. On the other hand, for parallel decomposition, you need to write. So I will not draw the structures. You can draw them. The structures are always used in direct canonic form, either the canonic direct or its transpose. As I said, since one is the transpose of the other, there is nothing like direct from 1 and direct from 2. These meaningless nomenclatures which have gone in the literature, we ignored them. Okay. So in parallel realization, on the other hand, you require to decompose h of z as summation hij, where hij is no more complicated than a bilinear, that is a linear divided by linear, or at the most it is a quadratic divided by quadratic. So biquadratic. You understand the meanings of this adjective bilinear and biquadratic. Okay. Now how to do this, how to break it up into different, one of the simple ways is to use partial fraction expansions, and that will ensure that you have real polynomials in the numerator as well as the denominator. In this particular case, for example, our partial fraction expansion shall look like this: h of z is equal to, now you notice that we cannot do with, this is not a proper rational function, right. So if I write a plus b z inverse divided by this plus c plus d inverse divided by this, it will not take care of the numerator. Is the point clear? We cannot write this as a sum of linear biquadratic plus another linear biquadratic, because the numerator then shall be of degree 3. Isn't that right? It is important to realize this before you carry out a partial fraction. How many factors, how many terms shall be there? Do you require a constant term or you don't require? Here you do require a constant term, otherwise you will not get the 4th degree in the numerator. All right. So our partial fraction expansion in this case shall be of the form A plus B plus C z inverse divided by 1 minus half z inverse plus half z to the minus 2 plus D plus E z inverse divided by 1 plus z inverse, the other factor, plus 1/3 z to the minus 2. Okay. Straightforward partial fraction decomposition. And then you, in order to find B and C, as I said, do not go to the complex calculations. One can of course do it religiously in terms of the complex poles here, then the residue shall be complex conjugate, and then combine the two and make your life miserable. Okay. What you do is you solve a set of simultaneous equations. You notice that h of 0, if you put z equal to 0, then this is infinity squared, this is infinity, so this term will be 0, this term will be 0, so it is equal to a. And from the given transfer function you can see that h of 0 is equal to 1. Why? Because z to the minus 4 divided by z to the minus 4, when you put z equal to 0, these are the terms that dominate, infinity to the power 4, and therefore the h of 0 is 1 by observation. Then you put h of infinity. H of infinity is obviously equal to a plus b. If you put z equal to infinity, then these two terms, these three terms 0 plus d, and that from the given function h of infinity is equal to 2, right? And therefore you have reduced 5 constants into 4. You have to solve only 4 simultaneous equations, which means that b plus d should be equal to 1. Okay. And by replacing d by 1 minus b, you reduce the set of equations to 3. Okay. Then you require 3 more equations, agreed? And the easy things to do are put z equal to 1. If you put z equal to 1, then what do you get? A plus b plus c divided by, half and half will cancel, 1 plus d plus e divided by 1 plus 1 plus 1/3, 2 1/3 is 7, 3, agreed? And you replace b by d minus 1 or d by b minus 1. Then the other one is h of minus 1. Very easy things to do. H of minus 1 is a plus b minus c divided by, if z is minus 1, then I get 2, agreed? This becomes plus half, this becomes plus half. So it is 2 plus d minus e divided by 1/3, that is multiplied by 3. What else can you take? You can take any number, but what is an easy number to take? Minus 1 we have already taken. Don't take a fraction, that makes life complicated. So you take 2, h of plus 2 or minus 2, okay? Then you solve these equations. I have done that. And the final results are as follows. Capital B is 0.3243. Capital C, please do verify this, minus 0.4595. I went up to 4 places of decimals. D is 0.6757 and E is minus 0.3604. 0.3604. So you get one parallel realization. Now, there is nothing sacred about this. How can you make a variation in this? You can distribute this constant into these two factors in any manner you like. So, theoretically there is an infinite number of variations. Okay? If you can distribute in such a manner that the coefficients B, C, D, E become fractions which can be obtained by shifting, okay, then you have done without multipliers. The aim should be to reduce the number of multipliers as much as possible, because multiplication is a time consuming process. For example, one of the solutions is, if instead of a equal to 1 you take a equal to 2 and take appropriate subtractions from these two terms, then one of the solutions that I worked out is the following. You can also write h of z, but your starting point is partial fraction expansion, starting point, taking care of the degrees of the numerator and denominator. Suppose the numerator here was of 5th degree instead of 4, then instead of a you shall have a plus b z inverse, and then you make the partial. You must be careful, keep your eyes and ears open. One of the solutions that I worked out is 2 1 minus half z inverse plus half z to the minus 2, and the numerator is minus 1.027 z inverse, no constant term here, plus 0.1216 z to the minus 2. I added a fraction in such a manner that there is no constant term. Similarly, for the next one, 1 plus, it just happens, coincidence, there is nothing sacred about it, 1 multiplier less, okay, 1 plus z inverse plus 1/3 z to the minus 2 minus 0.3063 z inverse plus 0.5856 z to the minus 2. This is one of the possible decompositions. There are infinite number of such decompositions that you can work out. I would like to point out to you that coefficients like 1/3 are nuisance because whatever way you truncate it, you are going to have error. 1/3 is 0.333333 recurring, okay, but coefficients like half, 1/4, 1/8, 1/16, or a combination, you can have half plus 1/4 plus 1/16, let's say. All of these can be obtained by shifting. Shift the number in parallel, okay, 3 shifts in parallel, and then add them together, accumulate. So, if you can express a coefficient as summation 2 to the minus I, you are very lucky, because you have speeded up the processing, the multiplication that is required. Now, as I said, the course is heavily obsessed with all pass filters. We now think of all pass realizations. In all pass IIR, all pass FIR is trivial. It is simply z to the power minus capital N. All pass FIR has the problem that the direct realization or cascade or parallel, they cannot be made canonic in multipliers as well as delays. No, in multipliers, delay is perfectly all right. For example, if I take an all pass filter first order, A1z is equal to 1 plus D1z inverse, D1 plus z inverse, then the canonic realization, canonic delay realization, you see this D1 and D1 are the same. So, it should be possible to do it only one D1, one multiplier. One multiplier and one delay should suffice, but the usual realization is, the direct canonic realization is z inverse then coefficient would be, multiplier would be minus d1, then multiplication by d1 and multiplication by nothing. Okay, this is the output y. You see that you require two multipliers. Now minus 1 is not a multiplier, simply changing the sign bit, we don't worry about it. But suppose due to quantization or any other reason there is a change in this coefficient as compared to this coefficient. Okay, suppose d1, this multiplier becomes d1 prime and this multiplier, let us say, remains minus d1, then the all pass property is disturbed, isn't that right? If the numerator d1 changes, then the pole and 0 are no longer in reciprocal pairs, and therefore the all pass property is destroyed. On the other hand, if we can make a two pair, digital two pair, in which the termination is d1 and this is multiplier less, this is our aim. We want to do with only one multiplier. This is multiplier less, then even if d1 changes, it does not matter, the filter still remains all pass. There will be a slight distortion in the delay, but the all pass property shall be kept intact. Okay. So, how to obtain at a digital two pair in which there are no multipliers? If we can do that, then we shall obtain a single multiplier first order all pass realization, and this can be obtained by an approach called multiplier extraction approach, and it is obvious what we are extracting. For example, if we had a second order, then we would have a d2p which has two multipliers, d1 and d2. Okay. We require this d2p to be multiplier less. This is no longer a digital two pair, it is a digital three pair. See, pair of terminals 1, 2, 3. So, we shall have to bring in the concept of digital three pair. Fortunately, we can do with the digital two pair only, we do not have to extend it. We will see how to do it. Now, you know that, let us draw this again, digital two pair, the multiplier is d1. What was the terminology? This we called x1 and this is y1, this is our input and output, and this was y2 and this was x2. And for a terminated digital two pair, the transfer function in terms of the transmission parameters is T11 plus T12 T21 multiplied by the termination, which is now D1, okay, divided by 1 minus T22 D1. All right. So, we shall try to identify the transmission parameters and then try to synthesize the digital two pair. That would be our aim. Okay. So, what we do is we simplify this 1 minus T2 to D1, then we get T11 minus T11 T22 minus T12 T21 multiplied by D1. Is this okay? Simplification. We compared this with what is given. What is given is 1 plus D1 Z inverse divided by D1 plus Z inverse. From this we try to identify the transmission parameters. Obviously, one choice for T11 is T11, put it equal to D1, all right, and no, I beg your pardon, what do you put T11 equal to? Z inverse, okay, because D1 has come here, agreed? D1 has come here, so you put T11 equal to Z inverse. Let's write it down. T11 equal to Z inverse. This happens to be the simplest choice. T11 is Z inverse and T22 shall be minus Z inverse. T22 is equal to minus Z inverse. And T11 T22 minus T12 T21 should be equal to minus 1, agreed? Or T1 to T21, see we have already fixed T11 and T22, and therefore we can find T1 to T21 from this relation, 1 minus Z to the minus 2. Now these two are fixed. Obviously we have a lot of flexibility with regard to the choice of T12 and T21, and the number of choices is virtually unlimited, but let me list some 4 choices and let us call them A, B, C and D. T11, T22, T12, T21. T11 is Z inverse, T22 is minus Z inverse, and for all of them these are the same. T12, one choice is let us take in T12 the total factor, then T21 should be equal to 1, agreed? We can also take this as 1 plus Z inverse and this is 1 minus Z inverse, or we can take this as 1 and 1 minus Z to the minus 2. We can take this as 1 minus Z inverse, 1 plus Z inverse. You can have many other choices, okay. Of these choices, obviously they will give rise to 4 different structures, and you can see and anticipate that because T11 and T22 are the same for A and C, it is same for all of them, but for A and C the T12 and T21 have a special property, they are interchanged. What do you think these structures shall be? The relationship between these two structures A and C, they are transposes of each other, that is C equal to A transpose. You can draw this structure and then verify this, but it is obvious from here that since T11 and T22 are the same and T12 and T21 are interchanged, it simply means that arrows have been interchanged, input output interchange, peak of node has been replaced by summer, summer replaced by peak of node, and that is how T12 and T21 gets interchanged. Similarly, B and D, D is equal to B transpose. We shall close this lecture here and